Hi, this is Rajatshukla from Perpetual Learning. Today I will show you what is a multi-active bridge converter, what is the difference between dual active bridge converter and multi-active bridge converter, what are the advantages, disadvantages and challenges associated with multi-active bridge converter, and my all contains based on this paper only. I am going to present multi-active bridge converter. This is the basic diagram of the multi-active bridge converter, where one of the DC to AC converter, another one is AC to DC converter, which is connected with common transformer core. Okay, so as you know that transformer, there are multi-winding transformer already available in the power electronics in the industries. So I will start from the basic electric bridge converter configuration. So there are H bridges are there, where one H bridge is consist of four switches. Let me show you the equivalent model. So this is one switch configuration. This is another switch. So this basic so element is called the MOSFET. This basic configuration is usually called the MOSFET. And so similarly there are four switches involved. So this common representation is normal H bridge, where this is the DC link plus and minus. So similarly this is the DC link is plus and minus. So and this is the middle point, and this is the middle point which is connected with the transformer. So this is the middle point I am taking here, let's say A and A dash. Here this H bridges configuration, if you make the dual electric bridge converter configuration, so you will see here the converter configuration will look like in this fashion. A dash, this is the transformer core, and this is the transformer second winding, and this is another H bridge where primary side is a DC input one source and another side is a DC output another output source. Okay, and this transformer terminal, let's say called B and B dash. Okay, so there are two H bridges which is connected with the single transformer. So this is called the dual active bridge converter configuration. Now if you are adding one another H bridge with the same core, so it will be look like in this way, what I am representing here. So there are third winding is necessary with the same transformer to connect this H bridge. So there are another DC source, let's say DC3 is called, and this is the C and C dash. So let's say this is a source bridge, and this is a load bridge, and this is a load bridge, where we have to maintain the phase shift phi in such a way that it should be this H bridge, this is the H bridge B1, let's say named is bridge B1, that it should be source bridge. Power should be transferred B1 to B2, this bridge B2 or B3 side. Okay, so here what observation we can see here, there are three bridges. So this is called the triple active bridge converter. Similarly, if you are adding the fourth H bridge, then that would be called, usually pronounced as a quad active bridge converter. So there, this become a multi-active bridge converter configuration, converter family. Multi-active bridge converter, the converter which involve more than two H bridges, which that is connected with the same transformer core. What is the difference between dual active bridge converter and multi-active bridge converter? You can see here exactly. There in dual active bridge converter there are two H bridges, but in the multi-active bridge converter there are more than two H bridges that is connected with the same transformer core. Here in this figure, the reactive network, that means if you are using a simple dual active bridge converter configuration, if you are talking about, there are one inductor term will come with the transformer, okay, which is the power transfer element. So this is called the reactive network here. Suppose if you add the capacitor, so this becomes a CL converter topology. So usually one of the famous topology of the dual active bridge configuration, that is called the CLLC topology of the dielectric bridge converter. So which type of this H bridge and this H bridge is the same, but the CLLC network you are using or simple inductance network you are using, this is a representation of this one. Okay, so let me show you what are the advantages of the dielectric bridge converter. Operation wise, here you can see here the DC to DC converter is operation wise. There are resonant and non-resonant types. So just previously I was showing you the resonant converter means CLLC or LLC type converter, and non-resonant means there are simple inductance involved with the transformer. Okay, and the architecture symmetry, that it means the symmetrical and unsymmetrical type, where the symmetrical means in the transformer the primary side, this area is a primary side and this area is a secondary side. So in the primary side windings or primary side number of H bridges, that should be equal to the secondary side. So this is called a symmetrical multi-active bridge converter. If the primary side H bridges is not equal to secondary side, as shown in the figure P, in this figure there are H bridges in the one side and the another the secondary side, that all remaining H bridges are there. So this is called the asymmetrical H bridges. So this is not necessary one H bridge is the primary side. There you can add more than one H bridges, but in this whole configuration, the figure B, that should be in such a way that primary side H bridges that should not be equal to the number of H bridges in the secondary side. So what are the advantages of the multi-active bridge converter? This is one of the biggest term. Okay, so before going to multi-active bridge converter, I would like to add one more point. There are, if you just think about it, there are two dielectric bridge converter and there are four H bridges with that is connected with the one transformer core. Which one will provide you the better power transformation and the better efficiency? That is a question mark which just ask in yourself after this presentation. Okay, so the advantage of multi-active bridge converter in terms of the core core material savings or core material reduction, you can see here that is shown in the figure below figure, in the bottom side figure. So here in the figure A, you can see if you are using the two dielectric bridge converter configuration, and then the transformer, this is a core type transformer. So you can see here this is the material which is here. That material you can save using of the multi-active bridge converter. So if this is a large area which is taking here in the dielectric bridge converter, this is the one of the issue that it is in, if you are using the two dielectric bridge converter for the different sources and loads, so the transformer core material is required high compared to the other one, compared to the multi-active bridge converter. So here the core material you can see here in the figure B is saving, it is the space is calling is a saving, and this you can directly add this upper side and lower side in the figure C. So what are the profit of this one? The profit is cost is saving because the material is not required here, and another one is power density also increasing because the core material reduction is here, and so the less core size is required. Okay, so this is another one answer why we use the multi-active bridge converter compared to the dielectric bridge converter. Okay, now just I had mentioned why we are using suppose there are two parallel to electric bridge converter and suppose one multi-active bridge converter there, then which one you will prefer? Okay, so the first answer was the material saving, the cost material saving, and the another answer was what will here I will show you. So the profit is here, you can see there is a common DC link, and common DC link is required to maintain to transfer the power from one side to the another side. you can see here in this bridges, suppose I want to transfer from position 1 to from position 2, so I need to use this common DC link. So I will transfer this DC to AC, this one dual active bridge converter, then DC link side, and DC link to the another converter side, another position side. So to transfer from position 1 to position 2, this secondary side, the DC to AC to DC converter, secondary side edge bridges is extra is adding. So the losses is increased because there are switching losses, conduction losses is involved, right? So I don't want to transfer it. So here the common core can easily transfer from position 1 to position 2 without using extra two edge bridges. Like this is acting like as a one dual active bridge converter from position 1 to to transfer the power from position 1 to position 2. This is acting like as a dual active bridge converter configuration. Okay, so this is another advantage if you are using multiple dual active bridge converter, if you are using compared to the one multi-active bridge converter. So this is the shorten the path. This is a very big advantage because less number of power stages it has to face, right? So this increase the efficiency here. Another thing, uh, what will happen, this is the third advantage. What will happen if the DC to AC network have some issues, some fault? Okay, so the reliability term will come here, and it will not exactly reliability, I should say, this is a fault tolerant capability. Okay, because it always be has a isolation cell, isolation switch, and this isolation switch, whenever this DC to AC, suppose this converter is having a some issue, okay, some fault condition is appearing, then this isolation cell will active and this bridge will be turned off. Another bridge will be acting as whatever they needed to transfer the power. Okay, so this will increase the fault tolerant capability of fault tolerant operation of the quad active bridge converter. This is the third advantage of the multi active bridge converter. The question is coming here, fault tolerant operation it is increasing. Why? Can we explain it more? I would like to, here in your screen, that this is the just screenshot of this. Let me show you one thing here. Yeah. So here in this paper, I have just taken these points from this paper. You can just read it here, or you can just go for more information. You just go here in this paper, and you can just get the information here. Okay, so I'm not exploring it more here. I'm just because I have just explained that isolation switch is here, because this isolation switch may be a 4-quadrant switch, or maybe a mechanical switch, or maybe a mechanical relay or something else. Okay, so I'm going to present in the next slide that is based on the challenges of multi-active bridge converter. So the challenges is very popular here in the multi-active bridge converter. There are only two challenges. So the first one is deviation is in the stray inductance. Deviation in the stray inductance means you cannot be design the multi-winding identically, which means their leakage inductance always be there different like what is showing here. So this is a two winding here, and this is another winding. So suppose you want to transfer power from this one side to this two side, and this is the third area. Okay, so this L1 and this L2 is transferring. Let's say the power is input here from this bridge. Let's say bridge B1, bridge B. Sorry, this is a bridge B2, and this is a bridge B3. So bridge B1 and bridge B2 is transferring equal power, which means P1 is equal to P2, and P1 is equal to P3. Here this is a bridge B1 and bridge B3 is transferring equal power, and here P2 is equal to nothing but 2 of P, where P1 is P2, that is equal to P, right? So So you cannot design this winding and this winding and first winding and third winding identically. Therefore, what will happen? L1 is not equal to L2. So you can, I mean, ideally you can transfer the P1 and P3 equally, but you cannot be do that in the practically, because L1 is not equal to L2, which affect the power, which affect the power. So power always be a deviate little bit. So what will happen? P1 is not equal to P2. P1 is not equal to P3. Therefore, P2 is just addition of the P1 plus P3, which means one port. I mean, this P1 will transfer. Let's say if L1 is less than L2, then P1 will be higher. I mean, suppose L1 less than L2, which means P1, I mean, bridge B1 carry the higher power P1, which means P1 is greater than P2. Then this draw a higher power compared to this one. So power balance is required practically in terms of the AC element design or control design side. Okay, so this is the one of the challenges which can solve by the another things. There are different research is going on in today's. What is the another drawback, or sorry, what is the another challenge with associated with multi-active base converter? Let me show you. Okay, this is one of the thing where unwanted cross coupling. What is the meaning of unwanted cross coupling? Suppose if you add with the same transformer, I mean with the if there are three winding, if I am talking about the three winding only, here third winding, this is the third winding. Okay, this is a name, let's say bridge B1, bridge B3, and this is bridge B2. Okay, so bridge B1 transferring bridge B2 power. So here let's say this is a dash, which means this bridge is appearing as like this single phase shift modulation. This is a a dash, this is a zero phase shift line, 0 degree line, where you are transferring the power bridge B1 to bridge B2 side. So this will look like in this way. There are some phase shifting. Let's say this is the 30-degree phase shift. Now this is the B dash, where this is called the B dash voltage. This is the voltage of B dash, which is appearing at the transformer terminal because of H bridge. Now VCC dash here. Now VCC dash is appearing here in this bridge side. Okay, now let's say in this way. This is the called VCC dash. So obviously you can see here this is a bridge B1, this is a bridge B2, and this is a bridge B3. So bridge B1 transferring the power bridge B2 side. I mean, let's say bridge B1 transferring the power bridge B2 side. And here you can see bridge B2 is transferring the power bridge B3 side. So you can see here bridge B2 is transferring bridge B3, that is okay. Bridge B1 is transferring bridge B2, which means bridge B1 is transferring the bridge B3 also. So bridge B3 is taking the power from bridge B2 and bridge B1 as well. What does it mean? Which means suppose bridge B1 is carry the 1 kilowatt power before connecting bridge B2 B3, then 1 kilowatt power will achieve by the bridge B2. But whenever you just connected the bridge B3 with the same core from the transformer with the transformer in such a way that it should take a 500 watt, then this because of this 500 watt or 0.5 kilowatt, it will add from bridge B1, because bridge B3 is highly lagging from the bridge B1. So this will not draw like 1 kilowatt, this will draw like a 1 second, let me change the color. So it will draw like a 1.3 kilowatt, let's say, and this will draw a 0.2 kilowatt here additionally. So 1.2 kilowatt kind of thing, and here it will be appearing like a 500 watt. So here you can see the bridge B1 is carrying high power compared to the bridge B2. In fact, this is undesirable thing. because I don't want to transfer the bridge B1 to bridge B3 power. I just wanted to transfer the power bridge B1 to bridge B2 only and bridge B2 to bridge B3 only. But because of phase shifting, unwanted cross coupling is appearing here. This is with the bridge B3. So this is called the cross coupling. How we can avoid it, and what are the another features? You can just read this paper, or you can see in the literature. There are so many things are available. If you have any query or any doubt, you can just log in with our web page, or you can join with YouTube or another things like Telegram, or you have another query, then you can just mail me using of this mail ID. Thank you.